Okay, good. Well, thank you very much for inviting me to this. I've had a great time interested in this. And we're gonna, this talk's gonna be about a different aspect of multi-messenger that requires a lot of patience. So we're gonna look at the new and improved Super-Kamiokande supernova alert, which was the subject of a highlights article in Nova, The Quest to Watch a Supernova in Real Time. At listening to talks yesterday, I realized I had to put everything in context, so I had to revamp things and put in a new slide. We're talking about the next nearby core collapse supernova. And so differences from other talks, when we're talking about supernovae, we're talking about galactic nearby in the Milky Way, the Magellanic Clouds. When we're talking about neutrinos, we're talking about bursts of ones to thousands of neutrinos. When we're talking about the neutrinos, the energies we're talking about in the order of 10 MeV, and burst durations on the order of 10 seconds. Now, I can't hide the fact that I was seething listening to earlier talks saying, oh, we have 10,000 events per day we have to sort through. And I was sort of very jealous about that because the number of burst events we've observed so far is 1. And how long ago was that? That was 1987. So we're not talking about big event rates that we have to sort through. We're talking about being prepared for a once-in-a-lifetime event. The estimated rate these occur, 3 plus, I was going to put down 3 plus or minus 3, but I thought that was a little bit cynical. 3 plus or minus something of these per 100 years. However, the science yield we can get from being prepared for these observations is priceless. So what we're dealing with when we have a core collapse is 99% of the gravitational energy released in the collapse going to neutrinos. We're talking on the order of 10 to the 58 neutrinos. We have different neutrino flavors with different fluxes. There's different stages throughout the supernova when neutrinos are produced. But from the viewpoint of an alert, the neutrinos stream from the stellar envelope before shock breakout. Challenges are distance. We have the inverse square law that works against us. But for neutrinos, we also have the problem of small reaction cross-section. So we need large targets to be able to detect meaningful number of neutrinos. But we have a huge opportunity not only with observing the neutrinos for the science we can get from studying the neutrino light curve, if that actually makes sense, but from studying that, but also to provide an early warning system before the electromagnetic radiation arrives at Earth, and can we provide pointing direction? So just looking at the scientific goals, if we can prepare to observe the first shock breakout radiation, and we can characterize it at multi-wavelengths. There's a huge amount of information we can get there, but also simply measuring the time from the neutrino burst detection to the detection of the first shock breakout can also give us a tomographic snapshot of the progenitor. So here's from a paper from Kissler in 2013, plotting the shock breakout time, neutrino time versus shock breakout versus the duration of the shock breakout radiation. We can see that we can, by looking at different sectors here, we can try and unentangle what the progenitor was. But we also see a problem. If the next galactic core collapses in a Wolf-Rayet star, we're talking about times of minutes from the neutrino burst to when we have to point. So that presents a challenge. I was going to go through this in detail, but I realized it would take 15 minutes to do that. There are challenges in the multi-messenger observation of following a supernova alert, the least of which is, not the least of which is the fact that these can be very dim. And when we have need to look at very deep magnitudes, we need often we have very small fields of view. So these are some of the challenges, and hopefully we can have some discussions on how to actually follow up the alert. So these early warning alerts from neutrino bursts, these can be from individual detectors. So what I'm going to be talking about is the alert from Super-Kamiokande, but also from combined alerts, such as a snooze producer. So these give complementary information. The reason I think it's useful to talk about the Super-Kamiokande alert is that we've recently done a number of upgrades, improved burst detection, some of which comes from the fact that we're now adding gadolinium to our water volume. We have improved pointing systems. We have a much faster alert generation, so a lower latency. So we used to announce within hours that we'd seen a supernova. Now we have an automated alert, which can give pointing information on the order of 90 seconds. And so I think it's important for us to discuss how this can affect our follow-up. So sorry for the last minute insertion with the poor font size. So if you're not familiar with Super-Kamiokande, this is a large water Cherenkov detector located 1,000 meters under a mountain for passive shielding in a mine. It's a huge detector, 50,000 tons of water. The outer, it's divided into an outer active shield and an inner detector, which is a detection volume, which has a fiducial volume of around 22.5 kilotons, surrounded by 11,148 photomultiplier tubes. And in the last couple of years, we've dissolved gadolinium in the water, and that improves our reaction channel identification. So here's the beauty shot if you haven't seen it. So if you look at the red on the left, that is two people cleaning the photomultiplier tubes on a little rubber dinghy. You see the globes of the 50-centimeter photomultiplier tubes. And so this gives us a sense of the size of the volume we need to detect these neutrinos. But to get there, there's yours truly at the entrance that you drive into the mountain. And for Lord of the Rings fans, I feel like I was going on the paths of the dead. So it's an interesting detector. So the way that these low energy neutrinos are detected, there's a few different reaction channels. The highest cross section is from inverse beta decay, where electron antineutrinos interact with the protons in the water, producing outgoing positrons. The outgoing positrons are almost isotropic, so they don't have directional information. Directional information is provided by electron elastic scatter, where neutrons of all type can scatter off of the electrons in the water volume, and they are forward scattered, so this gives directional information. We can also have charge current reactions with the O16 nuclei, and those are nearly isotropic as well. So if we have a neutrino burst, if you look at the black arrows, we think of a neutrino flux heading in one direction. If we have a supernova burst at 10 kiloparsecs, it's around 2,500 neutrino events that we'll detect at Super K. And so we have this flux of neutrinos, but the outgoing charged particles, positrons or electrons, think of the blue there. So they're being given off in all sorts of directions. Each of the events is individually reconstructed. So on the right, we see a Cherenkov ring. Usually low energy events don't give us such a clear ring, but from the detected Cherenkov photons, we can reconstruct the vertex and the energy and direction of the outgoing electrons or positrons. So the real-time supernova monitoring system works something like this. So we have the raw data of the different events and different backgrounds coming through. We search for event clusters, that is within 20 seconds, whether we have a cluster of neutrino events. And if we have an event cluster, we characterize its vertex and the number of events per cluster. and we can give off a golden alarm, which we send some information to snooze, but we also, because we have to reconstruct the direction, we also send out our own GCN notice because it takes place a little bit later. And so this has been improved. The reconstruction, I won't go through this, but this is a, I think, very clever way of using heel picks to actually find the supernova direction. I can explain that later. So I have to finish up quickly. So we now have a low latency between the burst and the notice being issued. We're at 90 seconds. We hope to bring it down to 60 seconds. The golden alarm, if we have a threshold of 35 events for the golden alarm, we can cover the small magellanic cloud. So that's very powerful. The direction reconstruction has been improved. Where we are now, if you look at the orange, if we use a event threshold of 6 or 7 MeV, we get slight differences, but we get around 3.7 degrees angular resolution, and that is in a 90-second alert. So that should maybe make us think about how we respond to supernova alerts. So before, committees, people getting together, hours later we say we saw something, snooze sends an immediate alert. We're a bit slower because we have to get the pointing information. So that pointing information gives us a great opportunity to observe the initial shock breakout if we're prepared. And so it's a once in a life opportunity. And so these are issues that would be worth discussing on how to respond to a supernova alert from Super-K and snooze. Thank you.